Hello developers, let's start developing. So today we're gonna continue with the solution for task 20 of the Advent of Code 2023. In the previous part we got up to a point when all of our simulation worked. It was able to simulate both the flip-flops and the conjunction modules and trigger all the events. However, we kind of messed up the order. So for the second example that we have, it's this one. We are running and we are pressing the button 3 times. So for the first button press, we get the exact same situation as it as we should get. Only it's on a bit different order. So we have these messages, these pulses that go through. The order is different, but the pulses are the same. And same goes for the second part. But only on the third press, we have this thing here. And you can see that we are actually outputting two high pulses. But let's see what the real output actually has. Well, we have this and this. So, because we are ignoring the clock and we're processing the first signal and then we're processing the second signal and we're processing the third signal, that means that we're going to get the wrong answer. We can actually do the code now and see that we actually do get an incorrect answer, but that's kind of beside the point. So, what I will do now, since now we have a disjunct set of modules that just happen to talk to each other. What we want to do, we want to actually change this into something else. So I will kind of change it. What I will do, instead of using a module map as our type that has everything, and it's just a set of modules, I will define another interface. And that will be our system. So the system has the modules. And instead of having we will maybe need some other parts inside our system, but we'll see about that. So we will have the system here, which is a system. And which means that we need to do this. Let's have this as the default because we will be replacing it once we get there. And it might be useful is the system is actually a class. Why not? We might want to add some issues onto it, and we will have a constructor that takes in the modules and we assign them. Cool. And we will actually route all our pulses through the system. So and not input and output, but from and to. And yeah, we kind of do something like this. So instead of having this is, yeah, let's just call it a new system of nothing. I don't want to have undefined. So this is a bad pattern that I'm just gonna use. As I mentioned a few times, in a real scenario, I would do something quite different. And we have the untyped as well, which doesn't actually use this, but it needs it. So now we have our broadcaster, flip-flop, conjunction, untyped module, we have oral modules, and we have our input processing that also has some errors. Because now we will get our module map, and then we're gonna say we have a system that will be a new system of module maps. One more thing that we need to do, we won't get a module map as the input. Instead, we will use our system. And it's generic enough that whatever we do, we're going to use our system. This is called system. Now, of course, we have errors across the board. But we're going to start with the input processing. So we defined our system, and that has our module map, but we also need to have a back reference to it. So the system has references to the module, and using classes we can get this done, that we have basically a circular reference. And we say this is good. And of course for the untyped modules we want to do the same thing. So we have all of our system, and at the end we're not returning that, we're returning a system. So we can be sure that all of our modules actually have the system as a thingy. Let's just console log it. And now we might not need the debug, because we use the debug to actually do that, but we'll say, no, we kind of don't need that. We can add a debug on the system. So let's see what happens. So instead of when we press the button, we are not actually doing that. We are doing system.receive pulse from us to that guy. Yep. Apparently we won't need any guard clauses. So here we have the exact same thing. We will remove the debug. We're gonna put it on another place. And instead of going from this name to output, yeah. So this exact line gets pushed here, only it's not pulse, it's high. It's not pulse, it's low. Don't need the debug. Everything else stays the same. The conjunction. Don't need the debug. That goes away. And this name, the pulse that we issue is a low pulse. And the same thing, and the pulse that we issue is a high pulse. I'm doing a lot of in-place refactoring, which means that I might have some bugs that we might need to take care of. But then again, we might not. So now at the very beginning, we add our button. So we have system.modules, and no, we don't want this. We do system.debug equals to true, or debug, which means that this has a debug property, which is initially false. Cool. Let's see if this thing happens. So we will trigger our button and see what happens. And we're going to push it 3 times. And since our system is not dispatching anything, we just get that the button wanted to send a message to the broadcaster. The system received this call and then just did nothing. It logged it to the console. So now we're gonna need to actually do that. And we will have a queue. We actually don't need a clock. Maybe a queue will be enough. Let's see. And this proposes to use a tuple. I never want to use a tuple. I will use just a pulse, which is a pulse, a from, which is a string, and a to, which is a string. And that's an empty array. So when we receive this, we just push this and process the queue. Something like this. Only which I can say. So now we might have a situation when we have a lot of methods calling each other. But no, we actually don't need this, since each receive triggers one next message. So this kind of keeps it synchronous. So we don't want this, we want an if here. So each message sent will trigger processing of the next one, of the first one. Let's see if this actually works or if I'm talking stupid things. This got processed in this way. Do we have any difference? Is that text available somewhere? It's not. So we're actually doing this thing. And I think that we kind of don't want to do what I've been doing. So this is what we are supposed to output. And this is what we actually did output. And I think we will see to do the two highs. So right now we are running everything through the system. But again, no, not this. I think I copied over the wrong. Yeah, this one. So yeah, we still don't have a thing. So we will need something like a cycle. How do we know when a cycle ended? So when we press a button, that starts a single cycle. Until we get that cycle, we need to just queue things up. Once all the things queued up, then we need to process the queue. And that will trigger more things. So we kind of need a clock as well. Mhm. So when we press the button, this triggers the first cycle. And here we have what happens. Let's see the clocks. So this is on clock 0. This happens on clock 1. This 2 happens on clock 2 because we go to on the inf and the con. And this 2 happens on clock 3 and this happen on clock 4. So we have 0, we have 1, we have 2, we have 3, we have 4. How do we know when we're done? So when we receive the first one, and we know that we receive it from the button, we run multiple receives per clock. So now the clock is 0. And I still want I can do if I put do something like that if I put a lot of logic in the system, but I don't want to put a logic in the system. I want the components to behave like themselves. So they are just calling to the system that I'm doing this. But maybe we can say, yeah, let's do that. So when it says the clock. No, I don't want this. I want this to be explicit. So each time when we receive, because we are right now, we have a situation when we're already receiving from the system and the system is only working to that, we're gonna take a clock. Yeah, that's gonna change our interface. So we're not receiving only that, but we're receiving on a certain clock. And now we can say, yeah, it's easy. So on that clock, which is a number, and then just say here, this is an event that should be done on clock plus 1. And the same thing here, and the same thing here, +1. And this, of course, this for now won't work because we're not using the clock. So we will have this process queue for this clock. And so this is not really a queue now. We can move it into a priority queue, but yeah, let's keep them that because we will say we will have events with different queues. We can just say, well, a more complicated code. Not those items, but we will also have clock, clock here. So these are events that should happen on that clock. So now we're saying that we're receiving an event that should happen on that clock, and we're saying, okay, now process for that clock. Find all of the items that are for this clock cycle. And it doesn't matter in which order we do process them. So we can say, and while real queue is that thing, we can say, no, we're not increasing the queue. We're going to shift from the queue. And we just check that. We might have missed somewhere a +1. So I will add the clock here in parentheses. And once we get this, actually, we're gonna need to remove those from the queue. So I will just say, or we can do this. We can actually transform it into a priority queue, which we sort all the time. So we can just have this. We don't really need the clock. Oh, we do need the clock. This. That we do need, and not only this, but now we need another condition that says if the queue length is 0 and the first one is from the current clock. But when we push something on this queue, all the time we say this queue sorted on the clock so that the ones with the lesser clock are above this. This is a weird bit of weird code, but we'll see how it works. Or if it works or if it ever stops working. Still doesn't work because we're doing 1, 2, 3, 4, 5, 6, 3, 4. Because we are generating 1, 2, 3, 4, 5, 6, and then we're going back to 3 and 4. So no, we need to basically, what I will do is this. Process if you have anything from the previous clock. Otherwise, don't do anything. And now it will stop on the first part because we don't have enough things. Yeah. We need to delay some processing. Basically, what happens is that yeah, clocking is a bit complicated thing. Hmm. We can add a method somewhere that says whether a component is done or not. So when this generates this, we don't need to process it immediately. We want to wait for this to also appear. And I guess we're running one more, so it's actually like this. And you can see that we do have all of them. We have the 1, we have the 2, we have the 2 3s, we have the 2 4s, only we have, oh, yeah, we have the 2 4s, we have the single 5 and the single 6. Everything is here, only not in the correct order. We have a bit of a race condition that always fails the way we don't want it. Really, I think I feel kind of silly because most of what I did was, I have a feeling right now that it's not actually needed. Why? And I think the cue is in the message titles. So when we receive a message, we just receive it. And after we finish receiving it, we finish receiving all the messages, we're gonna process the queue. So maybe we want to do this the other way. So when we push the button, this should start working. and then we need to run this. Now we're saying this, and the system can do we're adding to the queue, and this is actually kind of calling the receive method. So we are saying the process queue, the default clock is this should be 0 really. So when we're pressing the button, we're saying receive clock +1. This will be a special case when we actually press it with the same clock. Yeah, this is a direct thing. So that's one more difference between with the broadcaster and the button. So we're just saying button press and system process queue. And now we say we have that clock. While we're processing that, otherwise recurse, process the next system. And we might need to sort this. So let's see how it goes now. So we have the correct numbers for ones. We have 0, 1, 2, 3, 4, 5. And we have a proper clock. So button goes to broadcaster goes to A with a low, A goes with a high to inf and inf to B, high output, that's the third one. Then we go B to high B to low. Yeah. So let's actually remove this part. I will keep it here and run this thing. I will run it one more time actually, because we forgot to process the queue after we press the button the second and the third time. And let's have this once more. So we have this. Let's see if this matches anything what we have here. Of course it does. The second run. Do we have that? Oh, and you can see the second and the fourth run are actually the same. And the third run is different. Okay. And we have that as well. So it seems like we are kind of doing a good job on processing that. Now we can just say something along this line. Well, const loop target clock is 1000. No, that's not the target clock. That's actually something else. And we might need to reset the clock on each of these runs, but the target pushes of the button. So, and we can say while, or just use a for loop, while that is less than target pushes, button dot press it low, and we don't need the clock. And actually, we are setting the clock here. Let's do that. But if we don't specify it is 0, so each time it's starting over from 0. That's something that I didn't implement but got implemented on its own. So if we just do this, we can, it will work. But we're not in, but if we're not in a debug mode, if we just start this, we won't see anything because the system is just running by itself and nobody is looking at it. Come on, you're not supposed to be that way. You need to say that this is false. Oh, and we don't have a here. So we need to say if debug. Let's see it now. But now I think that we kind of solved this something in a very easy way because nothing happened. We ran through those 1000 cycles in 14 milliseconds. But what we actually want to count is the pulse count. So pulse counts. Those are, that's an object that has a low of 0 and a high of 0. So each time when we actually send out a pulse, each time when we call out system receive, we are sending out a pulse, we're queuing a pulse, and the pulse actually goes out each time when we do this line. So when we do that line, we just need to say pulse counts of pulse is increased by 1. I actually like this better because we have the pulse types, and after we're done, we can just say console log system.pulse counts. Let's see if the correct thing happens. Since we are working on the second example, we should have 4250 and 2750. 4250, 2750. Let's do it for the first example, which should be 4000 by 2000, I think. 4000, 8000 by 4000. So let's try that as well. Yep, seems about correct. And let's try this for this input. And that says that we will get that many and that many. So now we actually need to get the result, and the result is system.pulseCounts.high times system.pulseCounts.low. Or no, this is good enough. Let's see. I don't think that we should have an error in the multiplication. It's this biggish number. So let's see what is our system metric. If our system metric is correct, we click on submit and we are correct. And it was quite easy to be sure that we are correct because such a complicated thing really cannot be gotten wrong. So if we had some bugs, those bugs would have been obvious even with the smaller input. The final machine responsible for moving the sand down to island. Island has a module attached named RX. Oh, that's the module that bothered us. It's this one. A single low pulse is sent to RX. Reset all modules to their default states, waiting for all pulses to be fully handled after each button press. What is the fewest number of button presses required? Oh, now we don't really have a test case since we don't have the RX for anything else, but we'll see. So now instead of doing this, we need to do while true. And we're gonna have presses at 0, and we will say after you process the queue, count the presses. We will add something to the systems though. We will add a boolean that will actually take care of this. RX activated. And it will be false. So whenever we are sending something, we can just say if 2 is actually Rx, this Rx activated is true, console log at that. Yeah. So note that this will trigger both on a high pulse and on a low pulse because I want to see something. Because we might have a scenario when we're sending high pulses to Rx all the time, but the goal is to actually activate it a lot of now. So it seems that this happens a lot with pulse high, with pulse high, with pulse high. So and pulse is low. This Rx activated is true. And of course, since it only appears with KC, it's gonna be KC all the time. So we kind of don't need this thing. But if after each processing, we can just say this, not there, there. And of course, then we just return presses. And I have a feeling that this won't happen after a while. So I will say if presses is 1,000, then just so many presses so far. I don't have an idea of how to solve this aside from two approaches, and one approach is what we're doing. That is, we simulated the environment and now we're just running it until it finishes. If it finishes in a real time, we will enter that. If it doesn't, we will leave it run. The other way is to actually do this and do some analysis. What would it take in order for that to receive a low? Because right now we're around 500,000 of presses and this still hasn't happened. And with a system with this many things, we can easily say, actually develop something that will, I don't know, factorize a 2000 digit number or something like that. So the answer might be in the trillions or in the billions. If it is in the millions, I will definitely leave this running. No, actually, I will stop it. And since 10,000, 1,000 is kind of low, let's see how often we will see 10,000. It will either be 10,000 or 100 or 50, something that I can see that it's working, but it's not too chatty. Something like this, maybe 40. Why not? Not 40. 70, because 70 is a nice uneven number that will give me a lot of variation. Otherwise, I'm gonna see all even numbers, and who cares about that? So now every few seconds we get a new number. And in the meantime, we can try to, where is Rx? It's this one. So now we're gonna try to refactor it. Let's see, where do we have KC? So we have this and this. This is using KC, and this is using KC, and this is using KC, and this is using KC. And this is an AND, which means this will submit a low value when all of its input are so all of this needs to be high. Yeah, so now we have 4 values that their last input needs to be high. And now we're going deeper. What is pH? It's over there and over there. Are all of them in this? Vn, no. Kt, no. Hn, no. So Vn, yeah, only that. So we're 2 steps away. Kt, and note that we only have n's so far. Hn, okay, so at the very least we're kind of consistent. So let's start with MH. Ooh, and now we have a bunch of things talking to it. So this will be very, very complicated. So to be honest, I don't want to do it, so I'm not gonna do it. So far we've gotten to 5.5 million and it still haven't done. I would leave it running for a while and we'll see if it finishes. If it not, we're gonna cheat and try to read about the problem. Maybe we can get some insight about that. So the counter got right up till 50 million. So don't think that this will, sorry, I don't think that this will stop in the close future. So this will run for a while. But what I did find out by reading things on the internet, I didn't find it out myself. is that some people actually on Reddit said that this is very, very similar to the GraphVis format, which means that if you take this input and literally paste it into, I was not able to get GraphVis running on my Windows computer, but there is a very nice online implementation. It doesn't accept those special signals, so I had to remove them. And what I got was this picture, which is similar, very similar to pictures that other users have posted on Reddit and other places. So basically, we have some visualization like this one. So you can see what kind of happens. That we have a lot of flip-flops and kind of each flip-flop sense is halving the frequency of the previous flip-flop. So it's kind of counting binary numbers. If we have one flip-flop that goes 0, 1, 0, 1, 0, 1, the other on every 0 goes 0, 1, for example. So that means that we have a counter with two binary digits and so on and so forth. And this is great, but it doesn't really help me since now I will actually need to investigate each of the cycles and to see which cycle actually how it behaves. So each of these cycles have a certain let's call it cycle. So we will basically need to find out the cycle times of this, and this. So when this sends, what we need to find out? We need to find out when this will get a high result. So we have Vn, we have, this will only get a low result if this gets all of this high at the same time. And they emit all the time. So let's see when Vn emits. Uh, yeah, let's take them one by one. So I will kill this and let's see how long does it take for Vn to emit. Because once more, we have cycles that are independent of each other. So yeah, we're not gonna do only this. We're gonna have when Vn emits a high. Actually, let's add a private um, investigate or something like that. Or let's write it here. So when Vn emits, Vn is only connected to Kc, so if Vn emits, that means it emits to Kc. So if from is Vn, and we don't have the presses because the presses are not present in the system. But still, we can see whether that happens in what time frame. Whether it's 1 in 100,000 or, oh, and it happens quite often. But we don't care about that. We care about high pulses. It's quite often. So what we will also do, since we want to have the pulse here, we can have the presses inside the system. Actually, let's have the presses as a system property. We don't really care about that, or actually when we're gonna process it, then it becomes pressed. And I'm quite hoping that we will have a cycle. And I'm also hoping that that cycle is a prime number. Yep. So let's see. 3797 times 2 is that much. 3797 times 7. Let's say it's 26579. Yeah, we have a cycle on that side because one thing that you can see that all the sides are totally independent. So we can take a hacksaw basically and hack them into 4 different processors that don't have any kind of interconnection except for the broadcaster, which means they have independent cycles. So let's then write all of this down. So VH has a cycle, and we need to do the same for HN not NH, KT, and PH. You know what? I don't like it this way. I won't use console log. I will use another debugging thing. Outputs, which is a string array. Outputs.push. Let's just have them. And here we can say instead of stopping here, just break. And system.outputs.sort. And we can just use the default textual sort for off line of system output sort console log line. We should get something that looks maybe a bit better. At least it will be grouped by node. Of course, the sorting is wrong because that's how JavaScript rolls. So for KC, We have 4,000 that should go up. We have 8,000 that should go up. And we have this. Oh, I got it wrong. I was looking at Casey, and of course, all of them are Casey because all of them are going to Casey. But we have this many for HN, and then we have this many for this many for that, and that many. So for this, we only have 4021, and this has a cycle of, oh, it's obvious for this one because even I can multiply that. It has a cycle of 4021. And this has a very obviously as well because that's double that. A cycle of, and that is, yeah, it's triple that. A cycle of 4093. We should only have two of these because, yep, the cycle is 3907, and we have Vn, which we already saw that it has a very nice cycle as well. So we have those cycles. And now we can just ask Wolfram Alpha, but don't ask ChatGPT. ChatGPT has no idea what to answer when somebody asks him whether something is a prime number. This thing knows. So, 4021. Yep, that's prime. 4093. Yep, prime. 3907. Oh no. Prime. 3797. This totally smells prime. So we have cycles that begin from zero that actually are full cycles, and each of them are primes, which means that our answer will be. I don't have it in the code. I will try to have it somehow in the code by kind of sort of coding some assumptions, but we need to multiply this by 3907. Oh, so 4021 times 4093 times 3907 times 3797. It's this number which is the answer, so let's see. It is, we got until up to 50-ish million, so we would have needed to cycle for a while more. This is the index of the lowest number, I think, when the Rx will actually get a positive. So by mashing the button, we won't get anything. Let's see if this is the correct answer. And of course it is. So I'm feeling kind of cheated by this task because it needed to know this. And this would have been very, very hard to do by hand. I tried to do it, I gotten to this part, and then I realized it's gonna be a lot of time that I don't want to spend 2 hours of my life actually generating this. But apparently what was needed was to know that this is actually something called the GraphViz format. Fortunately, we were able to generate this image, and from this image, we were able to do that. Now, you might argue that we could have figured it out on ourselves because this thing is connected to those four, and those are, it looks like they're independent, but it's not obvious. Here's the Excel. it's very much not obvious. We would have gotten to it eventually by drawing it by hand, but it's not a fun exercise. And to be honest, the point of this is to be fun. However, once more, primes to the rescue, and we have our answer. I will try to have the code bring us the answer because, yeah, the answer is here, but it's not really obvious that it's here. I will try each of these to have actually at least two highs, and when they get two highs, then I calculate the difference, and that's the cycle, and then get the lowest common denominator, but they're prime, so the lowest common denominator is the product in order to actually have something that we can measure. Because right now we're running for this time, but basically we could have said, since we already know the answers, we could have said this thing. And my computer decided now that it's gonna make problems. Yeah. Sometimes computers don't like too much when you kind of work them over. So no, 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 no. I actually called it with the debug. That meant write out all the statements that you're going through, and that's gonna be millions upon millions of statements. Yeah. But from here we have HN, KT, PHVN, and now we can calculate all the cycles. So basically about 8,000-ish cycles are enough. But I don't want to count this as my timing. It should be actually calculated by the code. That's why we have code. So I'll try to get it a bit better, but don't forget, we have the gold star anyway. So keep developing and see you soon.